Hello, my friends, and welcome back to the Heavy Machinery channel. Today, we'll take you through the incredible manufacturing process of gigantic generators, showcasing the impressive engineering behind these massive machines. The 550 horsepower large electric motor rewind is a high-capacity service designed for substantial industrial motors. This process involves disassembling and rewinding the motor's stator windings to restore or enhance performance. Operating at 225 RPM and 2200 volts AC, this motor is typically used in heavy-duty applications requiring significant power and durability. The rewind service includes replacing worn insulation, repairing any damage to the windings, and testing the motor to ensure it meets original specifications. This rebuild ensures the motor can continue to perform reliably in demanding environments, extending its operational life and efficiency. Banding the rotor involves securing the rotor windings with metal bands to maintain their position and integrity during operation. This step is crucial before and after balancing to ensure stability and prevent movement that could lead to vibration or damage. It reinforces the rotor's structure, contributing to the overall reliability and performance of the motor. Before balancing, ensure rotor components are secured. After balancing, inspect and secure rotor for stability. Rebuilding the stator involves disassembling it and inspecting for damage. Damaged windings are replaced, and new insulation is applied. The rewound stator then undergoes vacuum pressure impregnation, VPI, to ensure thorough insulation with epoxy resin. After impregnation, the stator is coated with blue epoxy anti-corona paint to protect against electrical discharge and environmental factors. Excess epoxy is removed to ensure a smooth finish. This process restores the stator's performance and reliability, preparing it for reassembly. Vacuum pressure impregnation, VPI, involves placing the stator in a vacuum chamber where air is removed to create a vacuum. Epoxy resin is then forced into the stator windings under pressure, ensuring thorough insulation. This process enhances electrical insulation, protects against moisture and corrosion, and improves the stator's overall durability and performance. The stator is coated with blue epoxy anti-corona paint to prevent electrical discharge and protect against damage. Excess epoxy is carefully scraped off. The motor is reassembled by carefully aligning and securing the stator and rotor within the casing. The stator is installed, followed by reattaching the rotor and other internal components. All connections are checked and tightened to ensure proper operation. Finally, the motor's stationary runner is assembled and installed, completing the reassembly process before testing. The stationary runner is assembled by positioning it carefully into the motor casing, ensuring precise alignment with the rotor and other components. It is then secured using bolts and fasteners, and any necessary adjustments are made to ensure proper fit and function. Once installed, the runner is checked for stability and smooth operation before moving on to testing the entire motor. The motor is tested by running it under operational conditions, checking for vibrations, noise, and performance issues to ensure proper functionality. The design department develops electric machine layouts and optimizes performance efficiency. Laminations are thin, insulated steel sheets stacked to form the core of electric machines, minimizing eddy current losses and improving efficiency. In TES's production process, precise cutting and shaping of these laminations are essential for optimal performance in generators and motors. particularly in synchronous, asynchronous DC, and permanent magnet layouts. Laminations reduce heat generation and enhance energy efficiency. Welding ensures durable connections and structural integrity in electric machines. Toolmaking crafts precision tools for efficient manufacturing and assembly. Machining in TES involves the precise shaping and finishing of components for generators, motors, and other electric machines. It includes processes like cutting, drilling, milling, and turning to achieve the required dimensions and tolerances. Machining is critical for ensuring the accuracy of parts such as laminations and housings, enhancing performance and reliability. High-quality machining ensures seamless integration and longevity of electric machines across various industries. Machining checkup involves rigorous inspection of machined components to ensure they meet precise specifications. This includes verifying dimensions, tolerances, and surface finishes, ensuring parts align with design requirements for optimal functionality and durability in electric machines. Winding and assembly are critical stages in the production of TES generators and motors, ensuring the functional integrity and efficiency of electric machines. Winding involves the precise coiling of wire around a core to create the electromagnetic fields essential for the operation of electric machines. This process begins with selecting the appropriate wire gauge and material, which are crucial for achieving the desired electrical characteristics. The winding process is conducted using automated machinery or manually, depending on the complexity and scale of the machine. Each coil must be wound to exact specifications, with attention to uniformity and insulation to prevent electrical faults and overheating. Assembly follows winding and involves the integration of various components into a complete machine. This stage includes assembling the wound cores into the machine housing, aligning and securing them with other critical components like bearings, shafts, and end plates. The assembly process requires meticulous attention to detail to ensure all parts fit correctly and function together seamlessly. Quality control checks during assembly verify that all components are installed correctly and that the machine operates as intended. Together, winding and assembly ensure that the electric machines produced by TES are reliable, efficient, and capable of performing effectively in various applications, from green energy solutions to traditional energy sources and industrial drives. The test field is where TES generators and motors undergo rigorous performance evaluations under operational conditions. Tests assess efficiency, durability, and reliability, ensuring that each machine meets design specifications and quality standards before deployment in green energy, traditional energy, or industrial applications. Paintwork at TES involves applying protective and decorative coatings to generators and motors. This process includes surface preparation, priming, and applying multiple layers of paint to ensure durability, corrosion resistance, and aesthetic quality. Proper paintwork enhances the longevity of the machines and their resistance to environmental factors. Applications refer to the various industries and uses for TES generators and motors. These include green energy sectors like wind and hydropower, traditional energy sources such as diesel units, and diverse fields such as rolling mills, electric traction vehicles, and general industrial drives, each application demands specific performance and reliability standards.